Hello and welcome back to another HighPeak Education video. In this video, I would like to perform a calculation of a charged particle moving through a magnetic field and experiencing a magnetic force. Now, sometimes people call this magnetic force the Lorentz force, but I will just refer to it as the magnetic force. So, let's have a look at this problem. Aircraft sometimes acquire small static charges. Suppose a jet carries a 0.55 millicoulomb positive charge and flies due west at 660 meters per second over Earth's north magnetic pole, where the 8.00 times 10 to the minus fifth Tesla magnetic field points straight down. What is the direction and magnitude of the magnetic force on the jet? Okay, so a couple things to say here. First of all, let's start to write down our knowns in SI, the proper SI units. So suppose a jet carries 0.500 millicoulombs of charge. So that's a positive charge. Let's put that in red. So let's say Q, our charge, is, and let's get that in SI units. So that would be 5 times 10 to the minus 1 millicoulombs, which would be 5.00 times 10 to the minus 4 coulombs. Okay. Positive charge, it's flying due west. Okay. So if it's flying due west, we really should start to set a coordinate system. Okay. So let's do the velocity here, maybe in this purple color. Okay. So it's flying this direction. Let's call this due west. Okay. And this is the velocity vector. Okay. Again, this is west. And we're also going to say that the velocity magnitude, we know that. That's 660 meters per second. Okay. And it's over Earth's north magnetic pole, which we know the magnitude of that magnetic pole and that magnetic field. So that's B vector, because it's a magnetic field, and that has magnitude of 8.00 times 10 to the minus 5 Teslas. Okay? So, I mean, this would be like 0.8 Gauss, I guess. Yes, this would be 0.8 Gauss. Typically on the Earth's surface, we assume that Earth's magnetic field in general is about maybe 0.5 Gauss. So this right here is 0.8 Gauss. So near the Earth's magnetic north pole pointing straight down, it's a little bit larger. Okay, and then we also know it's going to point straight down. So let's call this right down. Okay, so it's going to be like so. Okay, straight down, and that's the magnetic field vector, B. So what are the direction and magnitude of the magnetic force on the jet? Okay, so the magnetic force we know should be F sub B. So we want to know the magnitude of F sub B. And we also want to know the direction. Now let's see if we can calculate the direction. So I think we should use right-hand rule 1. So let's point our fingers in the direction of the velocity vector. Let's curl our fingers in the direction of the magnetic field. And I think that the magnetic force vector should point, in this case, out of the page. So that means F sub B, that's the magnetic force vector, should point out of the page. Now, by the way, if the velocity vector was west, if the B vector, that's the magnetic field vector, is down. So I think that let's think about how this is going to work in terms of the cross product. So if B is out of the page, I think F sub B should point, think about this carefully, west cross with down should be perpendicular to that plane. So F sub B here should point due south. Due south. Let's see if I can draw that in a slightly different way. Let's suppose I draw a three-dimensional axis here. And the traditional way that people in GIS, so Geographic Information Systems, or in some sort of geoscience, earth science, or so on, typically orient their axes is like so. They orient, whoops, the positive x direction is to the east, and the positive y direction is to the north, and then the positive z direction is straight up. This is pretty common. So the positive z direction is straight up. Okay, so that's upward. Now, what we can say is we can say that due to the west, which is the velocity direction of the airplane, is in the minus I hat direction. So we can say, let's see here, that's the minus I hat direction because it's in the negative x direction. That's going to be cross product with the magnetic field vector direction, okay? And the magnetic field is pointing straight down. That's in the negative z direction. So that should be the negative k hat direction. I'm using unit vectors here associated with the three-dimensional axes. So minus times minus is a positive. But then we need to perform I cross k. Now hopefully you remember what I often call Matt's rule. I named this after my roommate in college. I've never heard anyone give this a name, so I decided to name it. Okay? Matt's rule says that for cross products, you should write out the unit vectors as ij, k, ij. If you're going to the right, it's positive. And if you're going to, whoops, just positive. And if you're going to the left, it's negative. Notice that I cross j would be positive k, or k cross I would be positive j, or j cross k would be positive I. But I cross k would be negative j, or let's say j cross I is negative k. But I cross I is 0, j cross j is 0, k cross k is 0. Hopefully you see how to use the rule. Okay, so a minus times a minus should be a plus, but then we need I cross k. So let's see where they're adjacent. Here's I cross k should be negative j. So this should be the negative j direction. So the negative j direction should be the answer. But according to this, the negative j direction should be south. So we confirm that that is the proper direction. Okay, so that's a couple ways to prove to yourself that that's the case. Otherwise, we should write down the equation for the magnetic force. Now, by the way, hopefully you notice that what is phi in this case? So phi is the smallest angle between the magnetic field and the velocity. So this right here is the angle phi. But phi, I believe, should be exactly equal to 90 degrees. And given that the equation is like QVB sine phi, we know what the sine of 90 degrees is. So we'll get to that in a moment. So let's write this out, because I know that many of you are learning this for the first time. So the magnetic field, the magnetic force vector magnitude should equal to, and then I'll put that sine phi over here, but it's going to be Q, so that's the charge, times V, that's the velocity magnitude, times B, which is the magnetic field magnitude, times the sine of the angle between the velocity vector and the magnetic field. Okay, so this can get moved over. Okay, so there it is. So I think we have all these values, so we can put them all in. Okay, so let's do magnetic force magnitude is equal to the charge in coulombs. That's 5 times 10 to the minus 4. Okay, so 5.00 times 10 to the minus 4 coulombs. And then multiply that by the velocity. Well, in this case, just the speed, the magnitude of the velocity. That's 660 meters per second. Okay. So then, let's also multiply by the magnitude of the Earth's magnetic field at this point. That's 8 times 10 to the minus 5 Teslas. So 8 times 10 to the minus 5 Teslas. And then we need the sine of 90 degrees. Now the sine of 90 degrees is a very special value from the unit circle and so on. That's equal to 1. Okay? Maximizes the cross product. So I think all we need is these three numbers multiplied. And we should be able to get that magnetic force magnitude. All right. So this is on and clear. We need 5 times 10 to the, that's second EE, minus 4 power times 660 times 8 times 10 to the minus 5th. We'll hit enter. We get 2.64 times 10 to the minus 5th. Notice that I think all of these are 3 significant digits, so we'll just write that down. So this should be 2.64 times 10 to the minus 5th. And it's a force, so the SI units are going to be newtons. Okay? So this should be our magnetic force magnitude. Okay? Now notice it's pretty small on this airliner. It's probably not going to deviate the airliner any significant course. Okay? Also note that we calculated the direction. So remember, this is the magnitude of the force, and we know that's in the southward. And the way we've set it up here, the southward is the minus j hat direction, or the negative y direction. But I guess what I'm getting at is I recommend that you calculate vector directions, often separate from calculating vector force magnitudes. You can certainly do them together. You could make this a vector equation and take the full cross product, but I think it's more cumbersome. Thank you very much for your attention. Hope that was helpful. Please smash that like button if you like this content, and please subscribe to the channel to grow the channel. Please share this amongst your social network. And thank you very much for watching High Peak Education. I will see you in the next video.